Hi, my name is Allison Coons, and I'm a solutions engineer with Hasura. Today we're going to talk about GraphQL and how modern APIs are used to power data-driven applications. If you've worked with data services before, you've probably used a REST API. The current industry standard, RESTful services, are a very common way for servers to provide data to applications over HTTP. To give a little context, we're going to take a look at a very common component of e-commerce applications, the shopping cart. We're going to consider the data required by this component and the work involved to provide it. Let's break it down. This single component actually incorporates data from a variety of sources. Product, the information about the item itself, like name and manufacturer. Inventory lets us know if the item is available, or perhaps warns us if only a few are left. Charges, calculations about payment. And order, the overall information about the cart, such as items and checkout status. These data sources may not be co-located in a single database or even managed by the same teams. For example, a company may have separate divisions for handling merchandise and orders. They may also use third-party services to help with things like calculating sales tax according to buyer location. From a front-end perspective, the shopping cart component requires data in a format that mirrors its subcomponents, with an array of item objects and a charges object. Creating this component won't take very long and has few opportunities for errors. Let's take a look at a very basic REST API call. The application sends an HTTP GET request to the server endpoint, in this case for products, and including the product IDs of the items in the cart. The API server sends back a JSON response with an array of products objects. You'll notice that this response includes a lot of fields that aren't being used by the cart component. This is a common situation with REST APIs known as overfetching. The API is returning data chunks, and the front end can use whatever it wants. Going back to the shopping cart component, we see that we'll need 4 requests to collect all of the data required. Of course, the responses will probably arrive at different times. In this case, the UI must show a loading state until all the responses have arrived, and the UI must be able to handle any possible combinations of errors and refetching. The front end will also be responsible for transforming the separate responses into something the component can use. For some components, like complex news feeds, this can get really complicated. Many companies invest in more sophisticated REST APIs. They can create custom endpoints for different services and components, returning the data in a more useful, predetermined format. They can also add optional fields and parameters to give the responses more flexibility. However, this is usually just shifting the work from the front end to the back end. Someone still has to add that functionality for each endpoint. The ability to make changes or add new features is also an important part of data-driven applications. Let's take a look at the process flow for adding a discounts feature to a shopping cart. First, we'll need to update the database with a discounts table and add relationships to any related tables, such as items or purchase history. Then, we'll need to create a new endpoint for discounts and update every other endpoint affected by the change. Each component will require a new version, and any new fields or parameters need to be added. All of these changes must be documented completely and correctly in order for other engineers to use them. Finally, the front-end engineers need to update every affected request with the new endpoint versions and query parameters. They might need to rewrite any data transformation logic as well. This can end up being a lot of work. Even a simple update, like a discount, might take an enterprise team up to a full month to get all the way through the development cycle. So now that we've seen the capabilities and pitfalls of REST APIs, what would we want a next generation of API specification to do? We can think of 3 overall pain points, right? Modern applications need to be streamlined, only fetching the data they need, and managing the amount of data transformations and compute required, even with very complex data. Companies also try to avoid needing huge teams and long development cycles just to ship basic new apps and features. GraphQL actually came out of Facebook, which came up with new tools for its own applications when focusing on emerging economy users with older devices and limited bandwidth. Since then, GraphQL has grown into a mature spec, overseen by the independent GraphQL Foundation, and an entire ecosystem of GraphQL client frameworks and tools are available. The biggest challenge of REST APIs, with complexity, can also point us in a very interesting new direction. What if we started thinking about our data as a graph? Going back to our case study, it's easy to see how our complex component actually has intuitive types and relationships. We have several unique GraphQL object types that rely on each other with one-to-one, one-to-many, and many-to-many relationships. Altogether, this creates our GraphQL schema and completely describes our data. We can build on this schema and automate a lot of the translation work between type fields and database fields. In GraphQL jargon, reads, writes, and real-time connections are called queries, mutations, and subscriptions. With the schema, we can also upgrade the developer experience with automatic documentation, auto-suggest when writing a query, and of course, requesting only the data you need. Let's have a little fun and see this in action. Here is a publicly available GraphQL API that serves Pokemon data. Publicly available data. We can fetch a list of Pokemon. Check out the auto-generated documentation. We have some options here. Change the query to request just a single Pokemon instead of a list, and you can see the incorrect fields being flagged and new fields suggested. Trim the data being returned, say if we wanted to power just a thumbnail list. And change the Pokemon. Take a look at this for yourself. It's totally fun. Let's go back again to our shopping cart. This time, we have an HTTP POST request to a GraphQL endpoint and a query, getOrder, with a single variable order ID. The JSON response is exactly what we asked for, and it will make it very easy to wire up the cart component on the front end. Even better, much of the work has been automated. We're not just handing it off to someone else. We can also see the difference in work required to ship a new feature. At this point, most GraphQL frameworks have the tooling to update a schema from database changes, or vice versa, and much of the endpoint update chores have been eliminated throughout the stack. After updating our tables and refreshing the schema, this is the only change required on the front end to power an updated shopping cart UI, which is great. The new feature development cycle has gone from a month to a day. What I hope you take away from this is that GraphQL is a great option in terms of greater efficiency for your data services, as well as engineering velocity, 2 key metrics for data-driven applications. So, you have some data, you have an application. Now, how can you create a GraphQL API for yourself? There are a few options out there, but today let's go for the one I work for. The Hasura GraphQL engine is an open source product that connects all of your databases and services to provide a real-time GraphQL API instantly. Several GraphQL tools have been written to automate basic CRUD operations, but Hasura took the unique approach of transpiling the GraphQL request directly into a Postgres operation. This way, you also gained amazing performance at scale. A Hasura GraphQL engine deployment can handle the same request rates and real-time subscriptions at a fraction of the cost. Hasura took things further by adding an authorization engine for highly granular security and many ways to define those roles and rules. Finally, Hasura GraphQL engine added actions, event triggers, and remote schemas, or federation, to provide outside data and business logic for full customizability of your API. Let's dive in. So the prerequisites for this project are a Heroku account, a Hasura Cloud account, and Postgres installed on your machine so that we can upload our dataset. First, create a new project on Hasura Cloud. Let's see how that looks. Next, copy this dataset to your new project. You'll want to download the dataset, copy the environment variable from your project, and then use that environment variable to upload the new dataset. It might take a few minutes to load. Finally, now that we have the data, we want to track the tables and relationships in Hasura. So launch your new console, navigate to the Data tab, select Track All Variables and select Track All Tables and Views, and then select Track All Foreign Key Relationships.